Now, this u can take in fact any value, but we will consider some special cases. So, if I take normal operation, for normal operation u is between 0 and 60 degrees. Now, what is so special about 60 degrees? See, 60 degree is actually the duration of one interval. See, we have defined what is known as interval. Each cycle of the AC side is divided into 6 equal intervals. So, one interval is 60 degrees. So, a pair of thyristor valves conduct for each of these intervals. So, u is less than 60 for normal operation. We will also consider abnormal operation where u can go beyond 60. Okay. So, let us first concentrate on the normal operation where u is between 0 and 60 degrees. So, if I take one cycle of the AC side voltage, one cycle of AC side voltage, any voltage, there are 3 voltage sources, 3 single phase voltage sources, any voltage, it is equal to 6 equal intervals. Okay. So, each of these are of duration 60 degrees. Now, what I do is I divide this interval into 2 sub intervals. So, each interval of duration 60 degrees is said to be equal to 2 sub intervals. So, there are 2 sub intervals, there is a first sub interval and a second sub interval in each interval. Now, by definition, the first sub interval is the one where there are 3 valves that are conducting, and the second sub interval is the one where there are 2 valves conducting. See, my assumption is normal operation, and hence u is less than 60 degrees. Okay. So, up to some angle there are 3 valves that are conducting that correspond to overlap angle or commutation angle, and once that is over, the current has completely shifted. Say, if you look at the previous figure, there is a certain duration for which 1 and 3 both are conducting. After a certain time, 1 stops conducting in the same interval, only 3 is conducting. Okay. So, I am dividing the interval into 2 sub intervals. The first sub interval is the one where 3 valves conduct, 3 valves conduct, and in the second sub interval 2 valves conduct. So, since you take any instant, either 3 valves are conducting or 2 valves are conducting, that is why this case is known as 2 and 3 valve conduction mode. 2 and 3 valve conduction mode. So, there are other possible modes corresponding to other possible range or other possible values of u. So, for u between 0 and 60 degrees, we have 2 and 3 valve conduction mode. So, if I want to analyze, I will take one interval, and we will see that it is sufficient to analyze one interval. We can in fact get the entire waveform of any quantity either on the DC side or the AC side. So, let me take one particular interval and analyze it in detail. So, consider the interval Can you suggest what interval we can take? See, one interval is 60 degrees. What interval can be taken? Any suggestion? Suppose I take the interval, the starting point of which corresponds to turning on of valve 3. At what instant valve 3 is turned on? Alpha. Suppose I take the interval between alpha and alpha plus 60 degrees. This is one interval. Okay. So, again this interval has two sub intervals. There is a first sub interval and a second sub interval. So, what is the first subinterval? What are the values of omega OT? What is the range of omega OT in the first subinterval? Alpha to alpha plus. If I take the second subinterval, it is omega OT taking values between alpha plus u and alpha plus 60 degrees. Okay. Now, I want to analyze the circuit for the two subintervals. Let me take the first subinterval. So, what I will try to do is, I take the first subinterval, that is alpha to alpha plus u, and try to draw the circuit which is only relevant for the first subinterval. See, the circuit is in fact drawn here already. Okay. Now, when I say first subinterval, there are three valves that are conducting, 1, 2 and 3. Now, there is a valve 5, there is a valve 4, there is a valve 6 which do not conduct. So, there is no current flow through valves 4, 5 and 6. In the second subinterval, when only in the second subinterval, which valves conduct? 2 and 3. So, when only 2 and 3 conduct, EA does not carry current, only EB and EC. So, what I will do is, I will just draw a simplified diagram where I only show those components which carry current. So, when something is not carrying a current, I can just remove it. Okay, it's a open circuit. Okay. So, I will just draw a circuit diagram showing only those components of the circuit which carry a current. Of course, all the three voltage sources carry current. So, I will show all the three. So, that means all the three inductances carry current. See, when all these inductances are connected in series with the voltage source. So, this is EA, EB, EC. Now, I draw the remaining part of the circuit in a slightly different way. If you look at the original circuit, thyristor valve 1 for this first subinterval alpha to alpha plus u is as good as being connected in series with EA and L. Similarly, thyristor valve 3, you please refer to the original circuit. So, if you look at the original circuit, 1 is connected in series with EA, 3 is connected in series with EB, and there is one more thyristor that is connecting 2 that is connected in series with EC. But only thing is, now the direction as far as 2 is concerned, the direction is in the opposite direction. So, the current flow is in entering, the current is entering the voltage source. Okay. So, this is 2. Now, from the circuit we know that the cathode of 1 and 3 are at the same potential, they are shorted. Cathode of 1 and 3 are shorted. So, I will short this. And the cathode of 1 and 3 is nothing but the positive terminal of the DC side voltage, and the anode of 2 is the negative side of the DC side voltage. So, on the DC side I have a current source ID. So, this is positive terminal of VD, this is negative terminal of VD. Okay. Fine. Now, let me take the current through valve 1, say I1. I1 is the current through valve 1. So, I will always show the current through a valve as the one which is flowing from anode to cathode. Similarly, I will also show I3. What about I2? I2 is ID. Please note I2, the current flowing through valve 2 is ID. Okay. So, that I need not give a separate notation for that. Okay. Now, For the analyzing this, I will apply Kirchhoff's voltage law to this loop consisting of voltage source EA, voltage source EB, the two inductances L, valve 1 and valve 3. Just apply Kirchhoff's voltage law, nothing more. Okay. So, if I do that, L d I 1 by dt minus L, okay, I will do one thing, I will try to go in a different direction. I will say L d I 3 by dt minus L d I 1 by dt. So, by Kirchhoff's voltage law, this is equal to EB minus EA. Is that okay? So, what is EB minus EA? See, we have the expression for EB and EA. EB and EA expression is given here. Okay. Yeah, it is root 2 V sin omega OT. So, I will make one further assumption, one further use of one further relation. So, d I 3 by dt into L minus L. Of course, I 1 is I 1 and I 3 are not independent. See, if I d is the current on the DC side, I 1 and I 3 are related to I d. So, I can write I 1 as I d minus I 3. I 1 is I d minus I 3 by Kirchhoff's current law at this note. So, this is d by dt of I d minus I 3. Equal to EB minus EA is root 2 V sin omega OT. So, I can try to solve this. This is a differential equation in I 3. So, solve this differential equation for I 3. That's all. Okay. So, this can be simplified. I d is a constant. Please note our representation of the DC side is a constant current source. So, I d is a constant. So, derivative is 0. So, what we get here is d I 3 by dt is equal to V by root 2 L sin omega OT. Is that okay? So, left hand side there is a 2L d I 3 by dt. So, the 2L I have taken to the right hand side, the root 2 gets cancelled with this root 2 on the right hand side. So, this is the expression. So, can I get an expression for I 3? So, I 3 as a function of omega OT. So, it is V by root 2 omega O L. You want to integrate with respect to, say, if you look at the left hand side, the derivative with respect to time. Say, for most of the waveforms, our independent variable is omega OT, but the derivative here that is involved is with respect to time. Okay, so, that is why there is omega OL coming there. Then what?
1 minus cos of cos.
Huh?
1 minus cos of omega.
1 minus cos. How did you get that 1?
Initial condition.
Plus cos alpha. Yeah. So, it is cos alpha minus cos omega OT. See, what you can do is take there is a constant of integration. How do you get that constant of integration? How do you get that? You use one condition, that is I 3 at yeah. So, at omega OT equal to alpha, I 3 is 0. So, using this condition you get the expression for I 3. Okay. Now, let me take this expression for I 3 and see what happens to I 3 at alpha plus u. Say alpha is at one end of the first subinterval, alpha plus u is at the other end. So, what is the value of, see, please note this expression is applicable for any value of omega OT between alpha and alpha plus u, that is all, not any value, it is not applicable for less than alpha or greater than alpha plus u. So, I 3 of alpha is 0. What is I 3 of alpha plus u? Okay. I can use that expression, but what is the value of I3 at alpha plus u? That is the definition of first subinterval. So, it is equal to ID. That means the current should have got completely transferred from valve 1 to valve 3. So, valve 3 current I3 at alpha plus u at the end of first subinterval is equal to ID. So, if you use the expression, what do you get? So, this gives ID equal to, so the expression is V by root 2 omega OL into cos alpha minus cos alpha plus u. Okay. Now, we normally write this in terms of current which is obtained as the peak value of short circuit current. Say, if you just go back to this circuit, the original circuit, see there are AC side terminals of the converter. Suppose there is a short circuit between any two AC side terminals. What will be the short circuit current through the source or inductance? Say, suppose I call this, say, point A, point B, C. There is a short circuit between A and B, or B and C, or C and A. What will be the current flow through the voltage source or inductance when if there is a short circuit? It is as good as saying I apply a line voltage. So, there are two phase voltages. I apply a line voltage to an equivalent inductance of 2L. Okay. So, I can easily get the RMS value of the short circuit current by taking the RMS value of voltage divided by reactance. So, the reactance will be 2 times omega OL. Okay. So, what I do is I define what is known as the peak value of short circuit current. We use a notation I subscript S, S for short circuit. So, suppose IS is the peak value of short circuit current. Then IS is related to the RMS value V, the frequency, angular frequency omega O, inductance L. Of course, I forgot to close this bracket. So, how is IS related to V, omega O and L? See, if you look at the RMS value of the short circuit current, it is equal to the RMS value of the voltage, which is RMS value of the line voltage is just V, RMS value is V, line voltage, divided by the total impedance or reactance, which is 2 omega OL. So, that is the RMS value. If I multiply this by root 2, I get the peak value. So, that is nothing but V by root 2 omega OL. So, I can write ID in terms of IS, that is what I am saying. So, I can write this previous expression as IS into cos alpha minus cos alpha plus u. So, this just for the sake of simplifying the notation, instead of every time writing V by root 2 omega OL, I just say IS, and IS has some meaning. Okay. Now, let us see what happens to the instantaneous value of the voltage on the DC side. So, if I take the first subinterval, what is VD? So, if you go to the equivalent circuit, see what we have here is the equivalent circuit, where only the elements which carry current are shown. So, what is VD? I can get an expression for VD from this circuit and the expression for I3 which I have just derived. Okay. So, can I get an expression for VD by applying Kirchhoff's voltage law to this lower loop? See, if 2 and 3 are conducting, obviously that happens in the first subinterval, they are short circuit, ideal intervals they are short circuit. What about the voltage across L in which is in series with EC? What is the voltage across the inductance which is in series with EC or valve 2? It is 0 because a constant current is flowing. dID by, see, rate of change of current is 0 because current is constant through this inductance L which is in series with EC. So, Vd can be related to EB, EC and the drop across this L which is in series with EB. Okay. So, by applying Kirchhoff's voltage law, I can write Vd as EB minus L dI3 by dt minus what? See, I am referring to this circuit. I am applying Kirchhoff's voltage law to this lower loop. So, it is minus EC. Okay. So, what is this L dI3 by dt? We have an expression for L dI3 by dt. Just go back to the previous page. L dI3 by dt is nothing but, can I relate it that to EB and EA? Yeah. Yeah. See, L dI3 by dt is nothing but EB minus EA by 2 from the first equation, because L di1 by dt with a negative sign is nothing but plus L di3 by dt. Okay. So, it is EB minus EA by 2. So, I have EB minus L di3 by dt is EB minus EA divided by 2 minus EC. Yeah. So, EB minus EB by 2 is EB by 2. So, I have EA plus EB by 2 minus EC. Now, EA, EB and EC are balanced. So, that means EA plus EB plus EC is 0. So, EA plus EB is minus EC. So, this is equal to minus 3 by 2 EC. Okay. So, this is the expression for Vd in the first subinterval. Now, if you take the second subinterval is very straightforward. Of course, it is much easier. In the second subinterval, I have only 2 valves conducting 2 and 3. So, if I want to draw an equivalent circuit showing only those elements which conduct current, then it is the same circuit which I got earlier, but now a few elements can be removed, because I1 will be, the current through valve 1 will be, in second subinterval I1 is 0. So, I can just remove this EA, L and valve 1. So, the remaining elements which are shown are EB, EC, L. So, there is a valve 3 which is shown and a valve 2 which is shown. ID and the voltage across this current source ID is Vd. Now, of course, showing L in this case is redundant because the current through the inductance is constant, both inductance is constant, its current is constant. So, there is no drop across the inductances. Okay. So, what is Vd in the second subinterval? EB minus EC, because there is no drop across the inductance. Okay. So, if I want the average value of Vd, can I get the average value of Vd from the expression for Vd in the first subinterval and second subinterval? See, first subinterval and second subinterval constitute one interval of 60 degrees. Now, is one interval sufficient for computing the average value of Vd? See, on the DC side, what is the minimum period?
Yeah, it's 60 degrees.
60 degrees. On the DC side, the minimum period is 60 degrees. Okay. So, we whatever happens for 60 degrees, the same thing repeats after every subsequent 60 degrees. So, the 60 degree period consisting of first and second subinterval is sufficient enough to compute the average value of Vd. So, I can say the average value of Vd. So, we will use this notation uppercase V with a subscript d. So, this can be obtained from the expression for the instantaneous value in the first interval of duration 60 degrees. So, it is 3 by pi, which is nothing but the reciprocal of pi by 3, 60 degrees is pi by 3 radian, into integral of Vd with respect to omega ot from alpha to alpha plus u plus integral of Vd with respect to omega ot from alpha plus u to alpha plus 60 degrees. Okay. So, you have to substitute two different expressions for Vd in the two integrals. In the first integral, Vd is minus 3 by 2 Ec. In the second integral, it is Eb minus Ec, and we have expressions for Ei, Eb, Ec. So, if I substitute those expressions, I get the, so I will leave it to you to derive that this Vd can be shown to be equal to Vdo by 2 into cos alpha plus cos alpha plus u. So, please derive this after substituting the expression for Vd and then afterwards substituting the expressions for Ei, Eb, Ec. Okay. Of course, Vdo is the notation which you have been very familiar with. What is Vdo? Is it the maximum, sorry, maximum, yeah, maximum average value of the DC voltage for which case? That we already, for the case of u equal to 0 or L equal to 0. Is it true even for this case? For any non-zero value of u, is it still applicable?
It's only a number.
Yeah, it is just a number. We have the we have the notation Vdo. What was the definition of Vdo? Vdo is the maximum value of the average DC voltage with L equal to 0.
Yes.
But can you still say that it is the maximum average value with non-zero L? Anyway, there is no need to even generalize the definition of Vdo. Once we have defined Vdo, we will just use it as Vdo being the maximum average value with L equal to 0.
Yes.
Okay. So, that same notation we are using here. Okay. So, we will just relate Vd to Vdo. Fine. Now, what was the expression for Vd with L equal to 0? See, L equal to 0 is equivalent to u equal to 0. So, if L is 0 or u is 0, Vd is Vdo. Vdo cos alpha, we derived that, Vdo cos alpha. So, you can get that, you just put u equal to 0, if u is equal to 0, we get Vd as Vdo cos alpha. Now, due to u or L, is there a reduction in Vd or is there an increase in Vd? There is a reduction. Okay. So, what we can do is we can actually quantify that reduction. So, what we will do is we will just use this relation to see how much reduction is there. Okay. So, yeah. So, since I am just going to the next page, I will use this. So, I use this expression Vd equal to Vdo by 2 cos alpha plus u. So, I will write this as Vd equal to, so without inductance, that is when L is 0 or u is 0, the expression is Vdo cos alpha. So, now I can write with inductance or with non-zero u, Vd is Vdo cos alpha minus Vdo by 2 cos alpha minus cos alpha plus u. Is that okay? This is same as the previous expression. Sorry? Sorry? No, I am just rewriting the previous expression. Instead of writing Vdo by 2 cos alpha, I am saying Vdo cos alpha minus Vdo by 2 cos alpha. That is all. I am just rewriting the previous expression, nothing more than that. Now, why I do this way is, The first term is the expression for Vd for the special case of u equal to 0. Okay. So, this can be written as Vdo cos alpha minus Vdo by 2 into cos alpha minus u. Now, just go to the previous page. Look at the expression for Id. Id is given by Is into cos alpha minus cos alpha plus u. So, cos alpha minus cos alpha plus u is Id by Is. See, from this equation, cos alpha minus cos alpha plus u is Id by Is. So, I will write cos alpha minus cos alpha plus u as Id by Is. That is what I have here. Cos alpha minus cos alpha plus u is Id by Is. So, we write this as Vdo cos alpha minus Rc into Id, where Rc is defined as Vdo by 2Is. So, one can put the expression for Vdo. See, Vdo is 3 root 2 V by pi. Vdo is 3 root 2 V by pi, and 2Is. What is 2Is? So, 1 by 2Is is 1 by 2 into the reciprocal of Is. So, by definition, Is is the peak value of the short circuit current. So, it is root 2 V in the denominator, in the numerator it is 2 omega OL. So, if you do all the cancellations, what you get is 3 omega OL by pi. Okay. So, the point to note is, if you just look at the previous line, what we have got is Vd is equal to Vdo cos alpha minus RCID. So, the second term is due to L, because RC is equal to 3 omega OL. If L is 0, we do not get the second term. Okay. So, that is why this RC has a name. RC is called commutation resistance, in fact, equivalent commutation resistance. Now, it is just an equivalent resistance, but it does not result in any loss. See, this resistance is not causing any loss. Say, there is no resistance in the original circuit. So, it is just a name. Okay. So, RC is just a notation. It is not a physical resistor which is present there which is causing any loss. Okay. So, one has to just look at that as an equivalent commutation resistance.